Hello everyone. Let's start with the backpropagation. So in my previous session, we understood how the forward propagation would work. Now we will understand how the backpropagation works to update the weight, right? So now if you'll see over here, uh, this is the output of my this neuron is 0.7164 after passing it to the activation function, right? And this was my error, right? So the if you'll see, my error is 0.08. So the output is my error. Now if I wanted to calculate in any application, if I wanted to calculate what proportion of my value of x would change or would impact the value of another variable, in that scenario we would be using a differentiation, which you have already studied during the calculus, right, in your academics. So for an example, if there is a pipe, and in the pipe you wanted to make a hole, and you wanted to find out how much hole we need to make so that the maximum water comes out from that particular pipe. So you are calculating a diameter of the pipe with respect to the volume of water which is coming it out. So here, if you need to update the weight, my uh, application would say how much weight we need to reduce it so that my error would get reduced and my prediction would give a better value, right, closer to the actual one. But how do we do that? Because there, if you see the formula of an error, it is the loss function, it is expected value minus the actual value ka whole square divided by the number of population we have, right? So in that calculation you have seen that there is no weight associated with it, right? So how do we calculate? How should we calculate the dy by dw? Because there is no direct linkage between an error and weight. So for that, the chain rule comes into it. So my error is dependent on an activation function. My activation function depends on a weighted average, and my weighted average depends on the weight, right? So my loss is y minus expected predicted value, right? My predicted value would depends upon the activation function. My activation function is 1 upon 1 plus a to the power minus x, right? And my activation function, the value of x, what we passed it over there was the weighted average, and this weighted average x1 w1, it depends on the w, right? So this is the chain rule we need to talk about. So now, if you'll see the dy by dz, I have just taken a simple case that y is equal to z plus 2 and z is equal to w by 4. And if I want to calculate the differentiation of dy with respect to dw, then we can also write dy by dw is equal to dy by dz, because y depends on z and then z depends on y. So dz by dw, if you separate cancel it, then it would gives the value of dy by dz. So if you wanted to calculate dy by dz and there is no direct relationship, then you need to calculate dy by dz and then dz by dw multiply with each other, it would give the value of dy by dz. So similarly over here, if you see, my loss function depends on an activation function. This E is a loss function. So I need to calculate the differentiation of how much weight we can reduce so that my error would get minimized, right? So over here, if you see, this is my error. My error is with respect to the activation function. This activation function, the second term is my activation function with respect to the weighted average, that is the net z, and the last one is this net z with respect to the dw, right? So we'll calculate each terms, and then finally we'll calculate the error with respect to the weight. So my first term is differentiation of an error with respect to the predicted value, right? So this what we are calculating it over here. So if you'll see what is my formula of an error, my error was this expected value minus the actual value ka whole square, right? So when you find the differentiation of DE with respect to the predicted value, it would come this 2 would come over here, it would get cancel it, and then finally it would come it as actual value minus the predicted value, and I'll take it as a ez. right? So what was my predicted value over here? My predicted value was 0.7164, right? You remember over here? So if you see over here, this is my predicted value, right? The value of y, that is 0.7168. So similarly over here, if you see, this is my actual value minus similar value, and if you, the differentiation of this negative value comes out, and the value of error with respect to the activation comes as minus 0.2836. Okay, so we'll keep it as it is. Now my second term, we need to calculate it, the activation function with respect to the weighted average. So what is the formula of my second term? That is dy by dz, right? So if you see the formula of activation function, it was 1 upon a 1 plus e ki power minus e ki power minus y, right? So if you calculate the differentiation of activation function with respect to this dy, it would come as a predicted value. I am not going into the differentiation part. You can go and check your calculus part, then you will be able to easily be able to do that. So it would come as the final value as this, the predicted value 1 minus the predicted value, right? So my predicted value is 0.716, 1 minus 0.716, and it would be 0.2031. Right. So this is my second term, and finally we would be calculating it z with respect to the w, and we know the value of z is x1 w1 plus x2 w2 and x3 w3. Right. So this is my formula, and when we'll do the calculus or a differentiation of this with respect to, so if you I'll just give you a formula that a x differentiation, if we take it, then the value would be given a, right? So when we'll calculate the see over here, when we'll calculate the differentiation of this with respect to this neuron, this would be my constant 0.5399, right? So my third term, if you'll see, when we'll calculate the value, it would be the constant value, and that constant value is the my value of an input parameter, that is a 5399, which we have calculated over here. Now we'll bring all this together in these three terms. This uh, DE, the error with respect to an activation function, it calculated as over here. If you see, this calculated as 0.2836. Similarly, over here, this would be calculated to 0.3, and this would be calculated as a 5399. And when we'll multiply this value, it would be this 0.021. So this means that this means that my error with respect to the weight means how much weight we can change so that my error would get minimized. This is minus 0.0201, would signifies that this much weight we need to change from the original so that my error would get minimized, and this is called as a gradient descent. So what is gradient descent? Gradient descent, the amount of a weight needs to be changed from the original weight so that my error would get minimized and get a more predicted value. So this is the gradient descent. Now we'll, in my next lecture, we'll try to understand how to update the weight from the original weight, and what are the different parameters which we need to consider it before updating a weight. Thank you.